Hello again. We looked at a dynamic problem where we wanted to maximize the stiffness of a structure by minimizing what is called dynamic compliance, and we found that the adjoint equation when there is a damping term will not be the same as the equilibrium equation, but it will become the same when you go backward in time, and that is what we were showing just before we ended the last part of the lecture. Now, let us understand this slightly differently. For that, let us take a different problem where we look at the meaning of this negative time that we took to say that we are going backwards in time, tau equal to minus t. Why was that necessary? That is apparent from here, but when we take another problem, that will become more clear. So, what we do now is take up a problem. Let us say we take a two-dimensional sheet of some kind, okay, that let it have some thickness. For now, let us take this as uniform thickness T, that is thickness, and we apply some electric potential difference between 2 points. Okay. Let us say somewhere here and here we apply, we fix it there mechanically and also apply some voltage. Okay. When you apply voltage and if it is a conductor, there will be current going through it. When the current goes, it will develop heating, what we call ohmic heating or Joule heating. Because of the heat, the structure will experience thermal loads and it start deforming. So, we would like to minimize that deformation. Okay. This is very common in electro-thermally actuated structures. What we are taking now are electro-thermal-elastic structures. Okay. We would like to make this structure stiff under such conditions, especially this becomes important if there are some holes in the structure. Let us say there are some holes in the structure. When I apply potential difference like that, current will flow in some fashion from there to here. Okay. Now, when that happens, these things are going to get hot and they are going to deform, and we want to minimize the deformation. Let us say actually it will be interesting to maximize deformation, but we will take a simpler problem of minimizing deformation. Okay. So, here we have 3 different energy domains: electro, thermal and elastic. Therefore, our problem statement is going to be little complicated because it involves 3 analysis in a sequence. We have to do first, we have to do electrical analysis, electrical, it is actually electrical conduction, because when you apply voltage to a conductor, the current is going to conduct. Electrical analysis, and then we have to do thermal analysis. It is also thermal conduction. In fact, the equation for both of them is identical with different properties. One will have electrical properties, other will have thermal properties, and then we have to do normal elastic analysis, which is what we have considered several times in this course. Okay. Now, how do I write this problem? I would want to minimize strain energy, let us say, because that will make me a stiff structure, stiffest structure. So, this is over a domain, let us call this 2-dimensional domain as some omega or area, whatever omega, and the strain energy is going to be half epsilon transpose d u epsilon, and there will be T the two dimensional area. Okay. What are these things? Epsilon here, this is not u, that should be epsilon also. What is epsilon? Epsilon is linear strain that we consider here, linear strain, which will have in two dimensions epsilon xx, epsilon yy, epsilon xy, will be epsilon xx, epsilon yy, those two are normal strains, and then epsilon xy with a shear strain. Where does that come from? Basically epsilon xx is I can just write, it will be dou ux by dou x plus dou ux, identical. I am just saying half and this, because that is how we generally write, because that applies to both epsilon normal strains and shear strain, dou u by dou y plus dou uy by dou y, essentially du by dou u by dou x. Xy, when you write, you will understand why I am writing like this. They will become dou ux by dou y plus dou uy by dou x, reverse. Okay. So, what are ux and uy? They are the displacements of every point in the x and y direction. 2D problem, there is some displacement in x direction ux, some displacement in y direction uy, and these things will vary from point to point. Okay. That is how we have strain energy. And what is the D here? The D is the stress strain matrix. If I multiply D with epsilon, I will get sigma. Sigma also will have 3 components just like strain has. So, this is 3 by 3, this is our stress strain matrix, or what we call constitutive matrix, okay, stress strain relationship. What are we changing here? We will change a fictitious term defined over the domain. At every point we have the indicator, this rho we can call it, it is not a mass density even though we are using that, it is an indicator function. What does it indicate? It indicates whether the material is present or not. If rho equal to 0, it is a hole there, rho equal to 1, material is present, material is present. Essentially by doing this, what we is, we are solving what is known as topology optimization problem. Okay. So, we have a function, okay, here rho is a function of x, y, x and y. We have the domain such as the one we showed. If I have at this point rho equal to 0, I get a hole there. Okay. If another point I have rho equal to 1, I will have material there. Okay. So, that way if I keep on doing this, I will get the holes and I will get solid things. Okay. This is, let us say this is all material, all this is holes. If I take thing, I get a hole. If I go here, I get material. If I get a thing, I will get a hole. If I go there, I will get a hole. That is how the holes get defined once we find this rho x y indicator distribution of the material function. Okay. Indicator function defines the material distribution. All right. So, these are all the things we had to define. Now, we are fine, we have defined the objective function and the design variable, and now we have to write the constraints subject to, we have to write the constraints equilibrium equation. There is epsilon here. So, that has ux uy that should be governed by some equation which we will write here in the so called weak form. That is, I would write this as epsilon transpose d epsilon v to indicate that it is a weak form, meaning that instead of ux uy here, I would take vx and vy, where v is the variation of u or it is a weak variable corresponding to u. Okay. We get this and then the t of this, and there is no mechanical load in this problem, but there is thermal load. So, that we will write it as epsilon thermal transpose d epsilon v t omega, that should be equal to 0. That is, for any arbitrary v, this equation should hold good. Now, what is epsilon Th? That is the thermal load. Okay, let's write it over here in a different color. Epsilon thermal loading, it's basically something that happens when you have thermal expansion, okay, that is strain, thermal strain. So, you have that as alpha into delta T, alpha into delta T and then 0. Only normal strain will be there, but not shear strain. Now, we have delta T coming in here, that is another state variable. For that, we need to have an equation. That equation is for the heat conduction. So, that can be written as follows. So, again that will be over the domain. So, we will write it as del T, where T is temperature, okay, that is a temperature rise, we will call it, transpose kth del T v, I call it, over T omega, right. So, again T v here is a weak variable corresponding to the temperature T, okay. So, we will have that. So, but temperature actually comes from the heat generated. So, we have to write that also here, that will say that is also integral over the entire domain, that will be del transpose T Ke, that is here it was thermal conductivity, it will be electrical conductivity into del this actually not T, that should be V, this is the Joule heating del V, and then we will have this T V here, and then the thickness this is equal, that is a weak form of the electrical thermal conduction equation, where this term that we have, this is the heat generation term, okay. It is like V square by R is ohmic heating, by R became electrical conductivity upstairs in the numerator rather than denominator. Then we are left with, we have T and now we have V, what governs V? So, we have another equation. So, let me write it in black like we have been doing. So, we have that will be the same equation V. Now, instead of Ke Th, we will have Ke and then del Vv T this, and there is no sourcing term, that will be simply equal to 0. So, these are the three equations. Corresponding to that, since these are functional type considered integral, there will be a lambda epsilon, and there will be sorry gamma epsilon, gamma T, and then there is gamma V, 3 Lagrange multipliers constants, and then we have the volume constraint that will be over this, not A, because we have rho. If I take that rho and integrate over the entire rho T, entire thing, that should be less than or equal to V star, the volume star. So, I will just put VL, because V we have used for potential, electric potential. So, I will say VL here, that should be less than or equal to 0. Here we will have the lambda corresponding multiplier for this. Okay. Now, let us take a look at this problem. Let me encircle the problem completely to see the overall structure. Okay. What is not clear is where is rho here, we do not see rho, but actually rho will be in the material properties, in this D and in this alpha that we have, and then kth and ke, all these places we will have rho. How does it come? Because of the way we define the indicator function rho. If I take the stress strain matrix, I will take the base material matrix as D0, multiplied by rho. So, rho we do not really make it 0, we take it something like rho min, okay, some small value, so that we do not run into singularity problems while solving. We take that rho. When it is 0, it is almost like a very weak material or very flexible material is there. When it is rho equal to 1, you have the base material. This we do for all the properties, that is alpha also will have alpha 0 into rho and so forth. K T H will also be K T H 0 into rho and so forth for K E also. Okay. That is only one there. So, we will put K E rho K E 0 equal to K E. So, we will have that. So, as rho changes from point to point, the material distribution automatically gets affected in terms of properties. So, when we have this, as usual we have to write the Lagrangian. It will be a long Lagrangian because you have 3 governing equations, 1 resource constraint, volume constraint and the objective function. So, if we write that, so first one is half epsilon transpose d epsilon T, that is a strain energy, and then we have this gamma epsilon multiplying the governing equation for the mechanical problem. So, we will write that epsilon transpose d epsilon v and T minus epsilon transpose, this is thermal d epsilon v. Then we will have gamma thermal that will be multiplied by del T del transpose T times K T H into del T V into T, and then we have del transpose V K U K E del V, that also will have T plus one more. So, all this is going to be the integrand, okay. And then we have del V gamma V, that will be similar, that is del transpose V K E del V V T, all of these things to d omega. We have put T everywhere, so that is okay, the d omega. This whatever is inside of these square brackets from here to here, the whole thing is our integrand f. Okay. Once we have this, we can write the Lagrangian for each of them. So, let me do it in RGB scheme. Let us I will do red color, I will do variation of this with respect to u, which is actually epsilon. I can say u or epsilon, that is equal to 0. When I say u, I have to put a u bar because that is a vector. Okay. So, we have u bar here, that is a vector. So, we have, if we take that, we look at wherever epsilon is that has u. So, we will just write it that way. Okay. So, that will give us this is like a quadratic term in epsilon. When you take variation, what I get omega, I will leave it in the weak form. So, I will get epsilon transpose d del epsilon, okay, and then T, and then here also there is epsilon. So, that will give us plus gamma epsilon del epsilon V d epsilon V T, and where else? I guess that is all epsilon is, and then there is epsilon thermal, but that will involve temperature. So, there is no u or epsilon. So, these things are there, this over the domain will be equal to 0. Okay. That is the adjoint equation. If you take with respect to rho, you would have got the design equation, but my intention is to show you that going backwards. So, in order to do this problem forward, we have to first do electrical problem and then thermal problem and then elastic problem, because if you look at the problem, if I cannot do the this problem first because it involves temperature over there. Then I go to temperature problem, I cannot do this because it involves voltage here. So, I have to first do this and then do this and then do this, that is a sequence. Okay. Now, what you will see for the adjoint equations is that it is reverse. You have to do the elastic first, then thermal, then electrical. Okay. Now, if you already see this, we can see that we can already do this first, not a problem. So, we can do this. To find what? We had to find our epsilon v or our v vector. The v vector is Vx and Vy. After you find Ux, Uy, then you would know this, and what we want to find is this thing at epsilon, then these are the weak variables for it. Okay. These are the weak variables or variation for epsilon v solutions. We can already solve it. We do not need to the adjoint equation with thermal and electrical field. Okay. Now, similarly, if I now go or let me choose green color, Lagrangian with respect to T equal to 0. Okay. We need to look at this where the temperature is in this and over here, and that is it, 2 places. So, this will be over that will be alpha epsilon thermal has alpha delta T, right, the temperature rise that we have. So, that will have when I do this gamma epsilon alpha, the T or delta temperature rise is taken care, and we will put like a identity thing there, because we need to retain that array feature over there into epsilon v, and well that time the T will be here anyway. So, that we have forgotten there. So, that T will be there, and it is there in the other term also, that will be gamma T and then del transpose delta T. Okay. That is what we will get. Okay. When we say here, this will also be, I should write it as better, I will write it as delta T. Okay. So, delta T, that is variation of T, delta T into k T h delta T v T, all of this d omega equal to 0. Now, if you see, this does not involve anything to do with adjoint variable of electrical thing. After solving this, I can happily solve this equation for this T v, because after you find epsilon, then we would know the epsilon and temperature, we would know that epsilon v is also known, and this is the one that we want to find, del T v over here and over there. So, that is known, because these are the so when I say we know this, what I actually mean is that T is known, but not delta T. So, this becomes the weak variable here. Okay. These are the weak variable. So, making that weak variable, if this has to hold good for all of those arbitrary weak variable, we can solve for T v. And third one that we have, let us go to blue now, Lagrangian with respect to V equal to 0, then look at all the terms that have V voltage. So, we have V over here twice, and then over there. So, we will get 2 terms, right. So, the first one, so we have to scroll down the screen. Let us remember this is gamma t times minus del transpose del v Ke del v, that will be a quadratic term. So, there will be 2 times this will be there, okay. That will be over, this will have a minus because that has minus there, del v transpose Ke del v v, okay, t, and of course, we have that gamma v, and this is a minus sign. Let me put that properly, minus sign t, that is the first term that we got where v is. The second term, okay, that is gamma v and then del t del v, and then we will have the rest. So, plus gamma v, sorry, this is actually not del v, this will be del gamma t, not gamma v, and this will be del transpose del delta v to k. So, here it is Ke, sorry, this came from Kth, thermal conductivity. So, let us look at the term we were writing. Oh, so that is actually, oh, that both is actually Ke. So, del v and then del v. So, that is, yeah, that is Ke here, okay, and this is also Ke, and then we will have del v v t, all of this integrated equal to 0. So, now when you want to solve it, we know v already. So, we know v, and we would have temperature coming in somewhere, okay, that in order to solve for this, we should have the temperature, this gamma t was there. So, here, okay, we missed a term when we are writing this, there was this Tv that we missed, okay. So, this should all be multiplied by Tv, and that will continue to be there over here. So, this will have a Tv. After we know that, we can solve this will be third. We cannot solve it first because we have this Tv term there. The Tv first has to be solved. In order to solve Tv, if we see this equation, we would have this epsilon v. So, first we have to solve for that and do this. Now, if you see, the equilibrium equation was electrical, thermal and elastic. Adjoint analysis is reverse, okay. So, let me just write that the sequence of solving the problem, equilibrium equations, and then let us say adjoint equations, the sequence, okay, that is what we want to do. Here we have to do first electrical, then thermal, then elastic, okay. Whereas here first we have to do elastic, adjoint one, then thermal, then electrical, okay. So, this is what happens when we consider dynamic problem. We have to go from 0 to t, the final time when we do equilibrium equation analysis, but when you do adjoint, then you have to go from final time to backwards in time to 0. That is what we see when you have sequentially coupled problems such as the one electro-thermally actuated elastic structures or electro-thermal-elastic structures. This goes in one sequence, this goes in another sequence, okay. So, when we do adjoint analysis, we have to keep track of how to do it, and that will be anyway evident from the equations that we write. Again, you remember that adjoint equations always have the same form as equilibrium equations. Only thing is that sometimes you may have to reverse the order, like in this problem electro-thermal-elastic, but also a dynamic problem that has a damping term, then you will get a minus sign in the adjoint equation. To get rid of the minus sign, you reverse the time and you get it the same as equilibrium equation. So, you can use the same framework, meaning the same finite element routine to solve this also, except that you go from, instead of going from 0 to final time, you start from final time and come back to 0 as if you are coming negative, which is what we see in the sequence of equilibrium equations and adjoint equations being different. Okay. Thank you.